Good day, everyone. My name is Xiang, and today I'm at the first Real-Time System Virtual Symposium 2022. And now I'm going to present the title that I received, which is the Processor Utilization Analysis of Non-Schedulable System. So the Processor Utilization Analysis is a feasibility test that is carried out to determine whether a set of tasks could be schedulable in the system by using the following formula. So the summation of all the UI must be smaller or equal to UN in order for the system to be schedulable. And for the real-time consciousness monitoring system that we developed in our project 1, we have 5 tasks, and I'm going to assign 2 parameters, which are the period and worst case execution time, and by using the rate monotonic scheduling policy. And I'm going to calculate the UI and UN for the task. So these are the parameters and computed UI and UN for each task. And as you can see, the value of UI for accelerometer is larger than the UN, so the system is non-schedulable. Let's move into the schedulability analysis tools. The purpose of the tools are to analyze a set of periodic tasks in the system and determine whether the system is schedulable or not. And the selected tools this time are the Cheddar, the time soup, and also mask. So here are some introduction to the tools, and I'll skip them due to time constraint. And this is the comparison of the tools. As you can see, 3 of the tools have graphical editor and they are open source. And also they have their own simulators which provide different functionalities. Only the times tool provides a code generator for the Cheddar and the mask above. These are the steps to carry out the processor utilization analysis using the Cheddar, and it will be included in the last part of the video. Okay, so this is the first research paper that I found, which is the rate monotonic analysis, the hyperbolic bound. So in the paper, the problem identified is the classical Liu and Leyland's processor utilization test, RTSE, is not that accurate. This test is the formula that we have included in the introduction. And when there's a high number of active tasks, the RTSE could fail on the physical task set. The proposed solution of the paper is to present an efficient test to perform analysis of large periodic task sets in dynamic environments with fixed priorities, and also to manipulate the feasibility condition to find a tighter sufficient scalability test as a function of the individual task utilizations. So here are some of the theorem proving and also assumptions, and I will not go deep into it. So after some theorem proving steps, we get this formula, which means that the product of all the UI plus 1 must be smaller than 2 in order for the system to be schedulable. For our research paper 2, the title found is the efficient schedulability test for real-time embedded system with urgent routines. So the problem identified is, in the case of rate monotonic scheduling policy and processor utilization analysis, the system utilization is only about 69%. Which is the limit for this function for large n. In the proposed solution, there are 7 new schedulability tests are described, and by using the assumed scheduling model, the system can use up to 83% of the processor compared to the 69% previously. Here are also some assumptions that I will skip. So as we can see, there are 7 tests here, and each of them have their own expression. So the system have to fulfill these expressions in turn to be proved schedulable. So the hyperbolic bound is chosen because the research paper provides a better and direct enhancement on the original processor utilization analysis, and it uses the rate monotonic scheduling policy instead of the earliest deadline first. And the theorem proposed is comprehensive and also is easier to understand. So I'm applying the theorem using the parameters in the project we defined just now. And as we can see, we compute the UI using this formula, and here is the result that we get. So by using this formula, we multiply all the UI we get just now, and we get 2.0706, and its value is bigger than 2, which means the system is not scalable using the hash bound, which is the same result as we get beforehand. For the discussion, the results are compared with the case study from the research paper by Chaori et al. And both the case study use the rate monotonic scheduling policy. For the autonomous mobile robot, it has 10 tasks, while our system has 5 tasks. It's using the response time analysis, while we're using the processor utilization analysis. It has a complex algorithm, which is this one, compared to our simpler algorithm. And the result of their case study is the system is schedulable, while it's non-schedulable for our system. And as a conclusion, we designed a set of parameters for tasks to achieve non-schedulable using processor utilization analysis. And 3 schedulability tools have been reviewed and compared. The Cheddar is selected to perform our schedulability test on the task defined. And 2 research papers on the enhancements are discussed, while the hyperbolic bound paper is applied to the set of tasks again. And our system is finally proven non-schedulable with the given parameters. And finally, the results of the paper is compared with the results of the research paper by Chaori et al. So that's all for my presentation. Let's move on to the demonstration of the Cheddar tool. I'm going to demonstrate the processor utilization analysis using our Cheddar tool. At first, we will need to create a new core
Afterwards, you need to create a new processor. We create using our core one. And we need to create a new address space for AP1. And finally, we'll need to define all our tasks. Okay, so after creating all our tasks, we can run our test now. Schedule from 0 to 120. So here's the timeline that have been generated. And now I'm going to perform the utilization test by selecting this feasibility test based on the processor utilization factor. Okay. So we cannot prove that the task set is schedulable because the processor utilization factor 0.79 is more than 0.74349, which is the same as our calculation before. So that's all for my presentation. Thank you.